everyone. So in the first chapter we discussed about the foundation of computer theory, and that we discussed why to study automata. We also discussed about the central concepts of automata theory. Now in this chapter we will try to understand what is deterministic finite automata, which we normally call DFA. In this chapter we will discuss about the various methods of representing DFA, the language of DFA, and also we will take some example to make the concept clear. So here comes the definition of DFA. Basically, DFA, that is deterministic finite automata, it is very limited in its capacity and is available with very limited space, or you can say no temporary storage is there. So we can see this type of automata is characterized by having no temporary storage. A finite automata is severely limited in its capacity to remember things during the computation. Also, the information can be retained in the control unit by placing the unit into a specific state. Now if we see the terms used in DFA, that is deterministic. So here the deterministic means that for every state and for every input there is only one defined output. Means there is no ambiguity. For every input to a particular state, we are reaching to a defined state. Finite means we have a finite number of states here. So the formal definition of DFA is defined in quintuple, or we can say it is defined by a set that contains 5 elements. That is Q. It is a finite set of internal states. Q represents the set of all the states that we are representing in our automata. Then sigma, it's a finite state of symbols called the input alphabet. So sigma represents a set of all alphabets or all input characters that are permissible in the given automata. Then the next is the transition function. For every automata, transition function is very important. This function tells us how to actually make a move in the given automata. To make a move in the automata, we have to take one state and an input, and as a result we get one state. So if you see in this is the transition function. This represents the state which is defined in this set, and when we put any input we will get one state. We will try to understand this transition functions by taking some example in the later slides. Q0 is again a element of this set Q, and this is a special element. We call it a starting state or a initial state. F is a set of final states. Here we have to keep one thing in mind, that in automata we have only one starting state, but final states can be one or more. So there F is basically a set that contains all the states that represent the final state. So in automata, when the end of the string is reached, the string is said to be accepted. By this, the meaning is, if we take any string that starts from the starting state, following the transactions of the given automata, and if it is able to reach into the final state, then that string is said to be accepted. So the transitions from one internal state to the other states in the given automata is defined by the transition functions, that is represented by this sign tilde. Now notations for DFA. So basically there are two notations for representing the automata. One is a transition diagram, which is basically a graph, and the other is a table. We call it transition table. So in transition table we will make the columns. One column is for the state, other is for the input, and we define that on a particular state, on a particular input, what will be the output. We will see this in the next example. So how to make a transition diagram? For each state in Q, there is a node. So transition diagram is basically a graphical diagram where we represent automata in a form of figure. Here the states are represented by a node that is represented in the diagram by a circle figure. We draw a circle to represent any node in transition diagram. For each state Q in the capital Q and each input symbol A in alphabet set, let the transition function Q comma A equals to P. The meaning of this is that for any state Q, when we apply any input A, we are reaching to this state P. Now here we have to note that Q and P belongs to this set. This is a set of states in a DFA, and this is a input that belongs to this sigma. This is an alphabet set. So the meaning here is when we provide any input to this state, we are reaching to the P. So to represent this, what we do is we will be making now this is a state, right? So we'll give the name as Q. This is the state, and when we apply any input A to this state, we are reaching to other state, that is P. So this is what is called transition diagram, and this is actually the representation of this, the transition Q comma A equals to P. So this is what the actual meaning of just a minute. Okay, so we'll take the cursor back. There is an arrow into the start state Q0. Also there is a notation. We have to put the arrow with the state that represent that it is the starting state. If I put this symbol arrow here, which is not coming from any state, then this state is said to be the starting state. Normally what we call it, we use Q0 symbol for a start state, and in the diagram we put this arrow symbol pointing to the starting state to assign that this state is a start state. And the states in your DFA which are having double circles like this, then that state is said to be a final state. So if any of the strings that starts from start state and is able to reach to the final states, then that string is said to be accepted. Now we'll take one example. DFA that accepts all and only the string of zeros and ones that have the sequence 0 1 somewhere in the string. Now first of all, we'll try to understand what actually the DFA means here. It accepts only the string of 0 and 1 that have the sequence 0 1 somewhere in the string. The meaning of this is that we have to design one DFA that can accept all the string that consists of 0 1 only, and it has 0 1 somewhere in the string. The meaning of this means if I write the string 0 0 1 1, this is accepted because we have 0 1 in between, or we can say 0 0 0 0 1 1 1 1 0 1 0. This is also accepted because the entire string is made up of 0 and 1, and we have somewhere 0 1 in the string. Now take another example. If I write 1 1 0 1 1 1, this is also accepted because we have 0 1 somewhere in the string. But let's take the other example. If I write 1 1 1 1 0 0 0, now this is not acceptable because we don't have the sequence 0 1 anywhere in this string. So this is not accepted, but this is accepted, accepted, accepted. So I hope you understood the question. Now the next thing is we have to think how we can design the DFA for this. So if we want to write the language, if we want to express this in the terms of language, we can write that a language L such that it is language L as a set of string such that W is of the form x01y for some string x and y consisting of zeros and ones only. By this I mean that this is the format of the string. This is the format of the string where it contains minimum 101. This x may be any combination of 01, y can be any combination of 01. So if you see this figure, this is the starting state, this is the final states, and the main focus here is we have to see is that we start from here, and the basic requirement is that the string must have 0 1. So we start, we read 0, we reach to some state, then we read 1, we reach to some state, and this is the final state because this string reads 0 and 1. Now later it can read any 0 any 1, before also it can read any 0 any 1. So this we have the DFA. Now here the question may also come to you that why not we make it 0 1 here and 0 1 here, because then also the string is accepted. Because if I read from 0 here and 0 0 0 or 0 1 or 1 1 and 1, now this is also correct, but now this is not deterministic. When I say deterministic means that for every transaction, for every input, we have the state is deterministic. It is determined where it has to move. Now if you see here from Q2, if I put 1 here also, then from Q2 on input 1 we can either go to Q1 or also to Q2. Means if I from Q2 if I input 1, now we have two options, either we can go to Q1 and also we can go to Q2. Now this is the ambiguity. So this is non-deterministic, that we will study that what is non-deterministic and how we can convert the non-deterministic to deterministic. Deterministic means that for every transaction, for every input, we have a determined state. We have a determined state. There is no ambiguity, no confusion. So just to make it DFA, this structure or this DFA has been drawn. So this is DFA representing basically this DFA will accept all the string that accepts the strings which has 0 1 somewhere in the string. So if you see this is actually the transition diagram. So as I told you that for the DFA we have two representation. One is the transition diagram. Basically this is the transition diagram. The other is transition table. This is the transition table. Now how to draw this transition table? Now this is the diagram which we have drawn. Now if we want to represent this diagram in the form of table, how can we do it? First we have to identify how many states are there. So we have Q0, Q1 and Q2. So we write the three states Q0, Q1 and Q2. Also this is the starting state. So we will write this arrow sign here that represent that this Q0 is the starting states. Now in this we have the alphabet is 0 1, means the permissible inputs are 0 and 1. So we make one column for 0 and one column for 1. Now we'll see from here. When we start from Q0, on input of 0 we are reaching to Q2. So from Q0 if we read 0 we reach to Q2. Similarly from Q0 if we read 1 we read to Q0. So from Q0 if we read 1 we read to Q0. Let's take another row. Now from Q1. For Q1 we see the transactions. For Q1 if I read 0, I read Q1 only. If I read 1, then also I am reading to Q1. Likewise for Q2, on the 0 input we are reaching to Q2, on the 1 input we are reaching to Q1. So this is transition table, this is transition diagram. If this is given to you, we can make diagram. If diagram is given to you, we can make a transition table. And remember that this star, this asterisk sign is to represent the final state, and this arrow sign is used to represent that this is the initial state, starting state. Now here we see what do we know about an automata that can accept this language L. Now the question here is how we can design the automata. For example, in the previous we have designed this automata, right? Now actually how to start with, because it is already made, it is given to you, but in the exam or maybe when you start from the scratch, how to actually identify that there will be three states are there and these arrows should be drawn like this. How we can come up with this? So here we need a little analysis and careful understanding of the problem. So we see here we must be knowing the alphabet set for a given DFA which we are going to design. For a given problem in which the DFA you are going to design, you must aware of the alphabet set. So here in our case the alphabet set is 0 1, means only 0 1 are permissible in the DFA. So in the quotient is given that we have to check that it can accept all the strings that contains 0 1 somewhere. So what we have to do is, when we start from the initial state, we have to, the state has to check that it has seen 0 1. If it has seen 0 1, then the reaching state is the final state. If it has not seen 0 1, then the reaching state is not a final state but maybe any internal state. So let us try to understand. Has it already seen 0 1? If so, then it accepts every sequence of further input. That means when you draw the transition diagram, when you start from the initial state, then after reaching to every next state, you have to check, the state has to check that it has seen 0 1 or not. If it has seen 0 1, then that reaching state is a final state. Otherwise, that is only a intermediate or internal state. has it never seen 0 1, but its most recent input was 0. Means we have reaching to state which have seen only 0 but not 1. That means if the next time if the state reads 1, it will reach to the final state. And the third case may be it has never seen 0 1. If it has never seen 0 1, then it cannot accept until it has read 0 and 1. So we have three basic conditions. It has either seen 0 1, or it has seen only 0 not 1, or it has not seen 0 1. So this is just a idea, means how to start drawing the DFA. The more examples we discuss, the more will be easy for you to understand. Then we have extended transition function to string. The extending transition function basically describes what happens when you start in any state and follow any sequence of input. If you remember in the previous transition definition, where I have told you that the transition definition is we are reading, we have taken Q cross alphabet gives you the state. This is basically arrow sign like this. Means when we on a set of on any state, if we provide a alphabet, then we reach to any state. So in this transition function we have one state, one character, one input symbol, and we are reaching to a state. But if we modify this, instead of one single input, one single character, if I take a string here, means a series of character. So if I say Q, an input of string, we write W for the string, and we are reaching to state Q, then this is a extended transition function. So normal transition function works for a single input value, but a extended transition function works for a input string, a set of letters, a set of input characters. So if this is our transition function, then extended transition function constructed from transition function will be called transition cap. So normally the notation for representing the extended transition function is this transition cap. This represents the extended transition function. So the extended transition function is a function that takes a state Q and a string W. So here we are inputting one state and a string, and then we are reaching to some state. The next is designing a DFA for a particular scenario. So it has given here, design a DFA which accepts the language L. Now L equals to W. L contains strings, words such that W has both an even number of zeros and even number of ones. So the question says that we have to design a DFA which can accept all the strings. It can accept all the strings which contains equal number of zeros and 1. That too, I can say even number of zeros and 1. There is no restriction of position, means they can occur anywhere. They can occur in the middle. No constraints is given regarding the position, but it is said that it contains even number of zeros and 1. For example, 0 1 0 1 is acceptable because we have two zeros, two ones. Or I can say 1 1 0 0 1 1. So this is also acceptable because we have four ones and two zeros, both are even. But if I say 1 1 0 0 0 1, so here we have three zeros and three ones, but they are not in even numbers. So this is not accepted, this is acceptable, this is acceptable. It should not be surprising that the job of the states of this DFA is to count both the number of zeros and the number of ones, but count them modulo 2. As you know that to find out the even numbers, we know in a programming logic, if we want to check that the number is even or not, normally we apply the modulus operation. So with the modulo 2 we can easily identify that the counting is even or not. So basically the states are counting the occurrence of 0 and 1, but simply they are not counting, but they are actually doing the modulo 2. They are counting the modulo 2 so that they can identify that the number of zeros and ones appeared is even or not. So if it is even, then the state that counts that number of zeros and ones is actually read by the DFA, then that state becomes a final state. So basically we see the figure and transition table, it will be easy to understand. So now if you see the figure, we have this state Q0 and is a starting state. Now when we read a single input here, so here we have counted that this is only single one, so this is not accepted. Now if we go back here, so we have two ones, that is even number, so now this should be accepted, so we make it, this is the final state. Now we'll check for the other possible strings. This is 1 0, so we are reaching to Q3. When we reach Q3, we have read 1 times 1 1 times 0, both is not acceptable. Now if I reach Q1, now how can I reach Q1? I can reach Q1 by, if I read 1, then this is 1 times 1, or if I say 1 0 1. So in this case we see that we have two ones but odd zeros, means 1 times 0 we have read and 2 times 2 times 0 we have read, but 1 times 1 we have read. So although 0 is fulfilling the condition, zeros are in even numbers, but 1 is an odd number, so the entire string is not accepted. But if you see 1 0 0 1, now if you see this, now in this 1 0 0 1 we have 2 times zeros and 2 times 1, means both are in even numbers, so this is accepted. So likewise same we can check it here. This is I start with 1, this I start with 0, and we can find that this state Q0 is the final state because it is fulfilling the condition that all the string is having even number of zeros and 1. So once this diagram is ready, we can easily draw the transition table by looking into this diagram. So if you see this Q0, now here you note that this is initial state as well as it is final state. Yes, this we can do it. So this is the transition table for 0 input. On Q0 we are reaching to Q2 and then Q1, and likewise we can make the transition table. So this is the transition table and transition diagram which accepts all the strings that have even number of zeros and even number of ones. Now this is called tracing. Here we are just checking manually that the string is accepted or not. Now so the transition is we have the transition table. We have the transition table here. With the help of this transition table we can trace any input, and we can see that on reading the input using the transition functions, are we reaching to the final state or not. If we are reaching to the final state, then that string is said to be acceptable, otherwise that string is unacceptable. So we see that we have to read the string 1 1 0 1 0 1. So if we see it, we can say 1 2 3 4 and 2. We have 4 number of ones and 2 number of 0. it should be accepted. But how can we prove it? We can do step by step. So where in the transition function we have the starting state. When there is no input, we are only on the Q0. Now see, when we read 1, now this is 1. When we read 1, we are actually using this. So how can we write? We can write transition Q0 epsilon 1. Now this transition I have taken from here. So this actually I am doing the inductive proving. So this is actually Q0. So I get Q01 Q1. Now so after reaching here, this is Q1. Now if I read 1 1 from starting, so we will check that Q0 1 1. How I can do it? I can do it with this, by using this transition. So I can say delta Q1 1, we are reaching to Q0. So the next is Q0 1 1 0. So likewise, if you trace the entire string, we can get that we are reaching at the finally Q0, and Q0 is what? This Q0 is a final state. So we can say that this string is accepted. Now let us suppose that after doing the last step, the last one, when we read this last one and we are reaching to either Q1 or Q2 or Q3, then we can easily say that this string is not accepted, because in our transition diagram this is the only final state. So if any string that is reaching to this state, that is called acceptable. And the language of DFA. The language of DFA is denoted by LA and is defined by LA equal W, such that Q0 W is an F. So the language basically is, for a given DFA, language is basically a set of all strings, those strings which are acceptable. Now when I say acceptable, means that if we read that string using the DFA, it should start from the initial state and reaching to the final state. So L is basically a collection of all the strings that are accepted by the given DFA, that defines the language of a DFA. So we can read here, the language of A is a set of string at the start state Q0 to one of the accepting state. If L is LA for some DFA A, then we can say that L is a regular language, or you can say the language for a DFA is a regular language. So for today, I think this is sufficient for today, and let me revise that today we have discussed about the DFA. DFA is a set that defines 5 elements: the set of states, the alphabet set, the transition function, the initial state, and set of final states. Then we have seen that how to represent the DFA using the transition table and transition diagram. We have seen actually how to start the DFA. We have taken 2 examples to draw a DFA that accepts all the strings containing 0 1 somewhere, and also we have discussed the second example to design a DFA that contains even number of zeros and 1. And finally we have also discussed the language. So the language of DFA is a set of strings that contains all the strings which are accepted by that DFA. Thank you very much. See you in the next class.